So if you've gone to the store and to purchase shrimp, you'll notice they come in different sizes. And it's kind of mysterious until you realize what they're doing here. So, you might have 41 to 50 count shrimp, or 10 to 15 count shrimp, or 82 to 100 count shrimp. Well, does that mean there's 82 to 100 in the bag? No, it means there's that many in a pound of shrimp. I don't know exactly why they do it, but that's how they do it. So 41 to 50 count means that there'll be anywhere between 41 and 50 shrimp per pound. They're not all going to be exactly the same size, but they're going to fall into that category, right? So if you have a smaller count, that means you have larger shrimp, right? We can count shrimp by weighing them. So if you weigh 2 pounds of 41 to 50 count shrimp, that's going to be 82 to 100 shrimp, right? Because there's this many in each pound and you've got twice that much. You're expecting a bunch of people for a reception or something and you need to get enough shrimp so everybody can have 5 or whatever. You're not going to stand there at the store and count shrimp, right? You buy the package, and from the package you can tell an approximate number. There are other things that are sold this way. Nails. At the hardware store, you can buy the little boxes of nails, but you can also go, especially to the old-fashioned hardware stores, and they'll have these big bins of nails. And you're going to take a scoop and you stick it on the scale and weigh it. And it's this much per pound because they know what size the nails are. And instead of counting all those nails, you just count them by weighing them. Any questions about that? So we can use a similar idea for atoms, except we're going to be more precise than for shrimp. Chemists often need to know the number of atoms that are in a sample of some mass. Why is that important to us? Because chemical reactions happen between individual particles. If you're going to make a water molecule, you need to have 2 hydrogen atoms for every oxygen atom to make one water molecule. And so you can't count atoms. So you're like, well, what mass ratio of these elements do I need so I don't have a lot of leftover of one or the other? So just like we count things by weighing them, in real life, we're also going to count atoms by weighing them. There are some units that are counting units. You probably know what a dozen is, right? A dozen is 12. 12 what? 12 things, whatever you're counting. Could be a dozen eggs is 12 eggs. A dozen donuts is 12 donuts. Sounds good. A dozen cookies is 12 cookies, right? Gross. Did you know that was a unit? Gross is a unit. A gross is a dozen. So a gross is 144 objects, 12 times 12. Another counting unit is a ream. You buy a ream of paper, 500 pieces. A ream, R-E-A-M. Yep. So instead of using dozen, because that's 12 and it's just way too small, even a ream is just way too small, we use a word, the mole, M-O-L-E. It has an abbreviation, M-O-L. Don't know why, but it does, so we'll just deal with it. But this is like the chemist's dozen. Just like the dozen means 12 of something, a mole means this many of something. 6.02214 times 10 to the 23rd particles. That number has a name. It's called Avogadro's number in honor of Avogadro, whose experiments led to the calculation of that number. So 1 mole of anything is Avogadro's number of units of that thing. Here it is with 6 sig figs. A lot of times we'll just use 4, 6.022 times 10 to the 23rd. A mole is a usable quantity of stuff. Okay, 500 atoms, you're not going to be able to see them. But if you have a mole of copper atoms, that would be about 22 pennies. You can hold those in your hand, right? Big enough to see, small enough to hold in your hand. A tablespoon of water is about 1 mole, 6 times 10 to the 23rd molecules of water. So this is a counting unit that is useful for the sizes of samples that we deal with. Any questions? Yeah. That's a good question. That's an excellent question. We'll get to that. So where did this number come from? Well, it's a made-up unit. 12 dozen is a made-up unit too. They all are. The value of the mole is equal to the number of atoms in exactly 12 grams of carbon-12. Does 12 grams of carbon-12 sound familiar? An atomic mass unit is 1/12 the mass of a carbon-12 atom. So how this works then is that 12 grams of carbon-12 would equal 1 mole of carbon atoms, which is this many carbon atoms. So this gives us a relationship between mass, grams of carbon, and number of atoms, and that allows us to count them. So the atomic mass of carbon-12 is 12 atomic mass units. 1 mole of carbon-12 is 12 grams. And so all of those average atomic masses up there do double duty. That's the mass in atomic units of one atom, atomic mass, mass of an atom. Or the molar mass, the mass of a mole, same number in grams. Any questions? Did that help with the previous question, kind of? So here we get into unit conversions again. So I think just because mole is just such a strange thing, nobody outside chemistry uses it. And you come in here and you're like, they're just doing this stuff, and sometimes you do it right and sometimes you do it wrong and you're like, I can't understand it. If you think about it in relationship to dozens, you can keep it straight. So I think all of you could tell me how many eggs are in a dozen eggs, right? How many eggs are in 5 dozen eggs? 5 times 12, right? If you can do that, you can do this, okay? So for eggs, we would use the relationship 1 dozen is equal to 12. Here, we're using 1 mole, 1 chemist's dozen is this many. And so we can have 2 different conversion factors. This number has to be entered using scientific notation on your calculator because no calculator that I've ever met will let you put in 23 zeros. So again, the times 10 part, the times 10 to the something part is the EE button or the EXP button. So a pure silver ring contains 2.8 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? Well, we're going to approach this like dimensional analysis. We're going to figure out what unit are they giving us? What's the number? There's the number, that many atoms. And what do they want us to find? Moles. So, funny dozen. So we will write down what we're given, 2.80 times 10 to the 22 atoms. And I can go from atoms to moles, just like I can go from eggs to dozen. So I only need one conversion factor here. Atoms to moles, and then in the bottom is going to be atoms, and the units will cancel out. They're not going to give you Avogadro's number in the problem. So here, if I think about a mole being like a dozen and atoms being like eggs, that's going to tell me which side to put the number on. Because you put the number on the wrong side and things go really bad. So mole is like dozen. So it was 1 dozen is 12. So 1 mole is 6.022 times 10 to the 23rd atoms. So get your calculator out, because this is one that if you're not using scientific notation, you're going to end up with a crazy answer. So 2.8 EE22 times 1 divided by 6.022 EE23 equals. And if you end up with something that's like times 10 to the 46 or something, you're miscommunicating with your calculator. Anybody need me to fix their calculator? Any questions? Yeah, a lot of these calculators have a button that it'll show you a fraction. It is great for math class. It's not very good in here. There's a way that you can make it show it to you in decimal. How many sig figs should that have? 3. So this number has 3 sig figs. Avogadro's number is not an exact number. We usually use it with 4. So this should have 3, so we'll call this 0.0465 moles. It's less than a mole. You can have less than a mole or something, just like you can have less than a dozen. You can have half a dozen eggs, right? That's 6 eggs. You can't go to the store and buy half an egg, right? They're going to sell you the whole egg or no egg, right? So we can't have less than 1 atom, but we can have less than 1 mole of atoms. So counting, and I kind of got ahead of myself earlier, to count atoms by weighing, we need the relationship between the mole and the mass, and that's the molar mass. That number is numerically equal to the atomic mass. The atomic mass is in atomic mass units. Makes sense, right? Atomic mass units. The molar mass is in grams. Same number. So we look on the periodic table, we see that the average mass of an aluminum atom is 26.98 atomic mass units. That means that there are 26.98 grams in 1 mole of aluminum, which is Avogadro's number of particles. Carbon atoms are smaller. So the same number of carbon atoms will be a smaller mass. And helium atoms are even smaller. Any questions? So the molar mass it's probably one of the most useful conversion factors that we have in chemistry. Converts between grams and moles of that element. And instead of memorizing a formula, this times the molar mass, or this divided by the molar mass, it's just dimensional analysis. The units will show you where to put the numbers, and that's a whole bunch of stuff you don't have to remember. Save that memory space for things that you do need to memorize. So for carbon, 1 mole of carbon weighs 12.01 grams. Those are equal, right? So I can make a conversion factor with 12.01 grams on top and moles on the bottom, or the other way around. I take one side and I put it on the top, one side on the bottom, and there's my conversion factor. And those conversion factors are just all sitting up there on the periodic table, waiting for you to use them. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. What am I given? 35.8 grams. And what do I want to calculate? Moles. Okay? So our path then is going to be from 35.8 grams, and we want to convert that to moles. The molar mass is the relationship between moles and grams, and so this is just a one-step thing. There's no other units in between. So 35.8 grams, 1 arrow, 1 conversion factor. What unit goes on top? Moles. Because this is Dora in her map, grams to moles. Well, she's having an easy day today, right? Grams to moles, just the one step. And then I'm going to divide by this unit because I want that unit to cancel out. The same thing we did with inches and centimeters. Exactly the same. I need numbers. They didn't give me any numbers because they're on the periodic table. This is copper. What's the element symbol for copper? Cu, not Co, Cu. So up there, it says 63.546. So that's the mass of 1 mole of copper. Now the question was asked earlier, do we use the number on that periodic table or do we use it on the one in our book? Which one do we use? Like I said, it doesn't really matter. But you should always use at least 4 significant figures. So this one has 5. If you want to round that to 4 significant figures, that's fine. The periodic table that I give you for exams just has 4 sig figs because that's good enough for our purposes. I have a bunch of these memorized to 4 sig figs just because I use them all the time. Copper's not one of them, so we'll just use this the way it is. So this tells me that the number here should go with grams. Grams is on the bottom, so the number goes on the bottom. That's equal to 1 mole, so 1 goes on the top. 35.8 times 1 divided by 63.546. 0.563, and it's giving me a whole bunch of numbers. I don't want to write them down. How many sig figs should this answer have? 3. We started with 3. This one has 5. Molar masses are not exact. So I need 3 in my final answer, so I'm just going to write down 2 more. And then I'm going to round. Any questions? So now we can count atoms by weighing them. So if we have the mass of the sample the grams. We can convert the grams into moles, and then the moles into numbers of atoms. So this is how we would count atoms by weighing them, which will make you do problems with, but then we don't actually do it much. It's important to understand the ideas. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon, and 1 carat equals 0.20 grams. What am I given? This 1.3 carat, right? That's not the crunchy carrot that you eat that's orange. That's a unit they use in diamonds. And they're giving us this relationship. And what do they ask us to find? How many atoms? Right? So I have two things given to me. 1.3 carats and 1 carat equals 0.20 grams. Which one of those cannot be used as a conversion factor? This one, right? That's just a unit. This is the one we're starting with. Maybe let's highlight that one in yellow. That's what we're starting with. We were given this, but it's going to be a conversion unit a conversion factor. So we're starting with carats and we're going to atoms, right? And then we have to figure out the steps in between. Well, we probably need this one. This would allow us to convert carats into what? Grams. Carats to grams. And then to get from grams to number of atoms, it's the new unit we learned about today, moles. Grams to moles and moles to atoms. 1.3 carats, 3 fractions, because there are 3 arrows. So if you're still feeling a little iffy about dimensional analysis, hit me up tonight and we'll make the light bulb come on. And then this will be easy. Carats to grams to moles to atoms. Carats to grams to moles to atoms. I put the first unit in the bottom, so it'll cancel out. And then I put this guy in the bottom, and then this guy. I want all the units except my ending one to go away. Put all the units in first, and then put the numbers in. Well, I've got this one. 1 carat is 0.20 grams. Grams is on top, so the 0.20 goes with the grams, and 1 carat goes in the bottom. There's no thinking. The units tell me where to put the numbers. Moles and grams. Where do we get that from? Periodic table, right? Diamonds are a form of pure carbon. What's the mass of 1 mole of carbon? .01 is with 4 significant figures, and that one's going to show us 0.8, so we could use that. Atoms and moles are like eggs and dozens. Atoms are the eggs, and moles are the dozens. So as always, 1 dozen is 12 eggs, so 1 mole is how many atoms? Avogadro's number, 6.022 times 10 to the 23rd. It's long, and I usually don't leave enough space, so it just kind of angles up like that. So now we know what to do. 1.3 times 0.2 divided by 12.0108 times 6.022 EE 23 equals. And it's going to give me a big long mess. I'm going to write the whole thing out just so you can see what it looks like. Now, if you're not paying attention, you may not notice that there's an E in here. That's how my calculator tells me this number times 10 to the 22nd power. Different calculators express it differently. But always check the end, because otherwise you're going to say that this is 1.3 atoms. That's like telling me you have 1.3 children.
On the test, if we wrote our answer out with the calculator just like that.
With the E?
Yeah.
I understand what it means. Yeah. But if it's multiple choice, it won't look like that. Yeah.
Well, you have like free response?
I do have some free response.
So that would be okay.
It would be okay. But it's like baby talk. So when one of my sons was little, we were at a restaurant and he kept talking about the dollar biller. Anybody, can you guess what the dollar biller is? The cash register. The dollar biller. Well, we finally figured out what he meant. So then we understood him, but he called his big toe his fat toe. Right? So writing it out with the E is like baby talk. I understand what you mean, but let's practice using human math language instead of calculator language. Okay? So again, sig figs. This time we started with 2. This conversion factor only had 2. These guys had more, so it's going to be 2. So 1.3 times 10 to the 22 atoms. Anytime you do a calculation and you get less than 1 atom, something went wrong. Yes? No, actually it's not. Carat is the size of a diamond. It's the mass, really. Oh. I never noticed that. That's possible. Because if you do a different number of carats, all these other numbers are the same. And if that one didn't change, then the other ones wouldn't either. Now I'm curious. We're going to have to look that up. Never noticed that before. Thank you. Any other questions? Are we done yet? No. I think we're almost done then. So I was trying to help you understand how tiny atoms are, and now I'm trying to help you understand how big Avogadro's number is. My kids had a book called How Much is a Million? And it talks about, like how long would a million pieces of spaghetti be? And it's really fun. What? Yeah, I kind of think there might be a connection there. So if you had Avogadro's number of pennies, it would cover the Earth to a depth of 300 meters. That's 100 yards the length of a football field. The entire Earth covered in pennies. It's a lot of pennies. That many grains of sand cover the whole state of Texas to a depth of several feet. If you counted 1, 2, 3, 4, 5, 24 hours a day for the rest of your life, never took a break, you wouldn't get to Avogadro's number. The national debt pales in comparison to this. This is just an unbelievably large number. And here it is, written out. And I know, this is thousands and millions and billions and trillions and quintillions, quadrillions, hexillions? I don't know. I don't think we have a name for that. It's really, really big. Oh, okay, this is the last one. We can do it. Just one more and we'll be done. So this is a critical thinking problem. So we've done things with volume a little bit, and length times width times height, and we've done things with units, and now we've done things with atoms and moles and stuff. And so here is colliding those things together in a way we haven't seen before. You're not immediately going to know what to do. So don't expect that. Say, okay, I can do this, So we're going to read the question, we're going to pick out what was given, and then we're going to start thinking about it. So a titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. Well, I'm going to highlight the numbers that they gave us. This many atoms, and this density, and it's titanium, that's important. And what are they asking for? The edge length of the cube. Some problems can be done with just dimensional analysis. Other problems can be done with just an equation. And sometimes you have to do both. Remember the Antarctica problem? Yeah. This isn't going to be that messy. So they're telling me there's 2.86 times 10 to the 23rd atoms. And they're giving me this density, 4.50. That's a fraction, grams per cubic centimeter. Grams over cubic centimeters. And if it bothers us that there isn't a number there, it would be a 1. And then over here, I'm trying to get to the edge length. Well, what kind of a unit might that be? It didn't specify. Centimeters, right? So centimeters would probably be good. What do we know about the relationship of an edge length of a cube to anything else about a cube? The volume of a cube is L cubed. Because with the cube, the length, the width, and the height are all the same. So this is L. So it's L times L times L, L cubed. Okay? That's something that I hope you would remember. But an equation like that might be given on an exam. So basically, I'm trying to find the edge length, L, and I know that it's related to the volume. So if I had the volume, then I could find the edge length, right? So what I need to get is the volume, and what's a good unit of volume here? Cubic centimeters. Now this is going to be an equation, so I'm going to make that a different looking arrow because that's not just going to be a conversion factor. How can I get from atoms to cubic centimeters? Moles and grams. Yeah. Here's a clue right here because this is grams and cubic centimeters. Here, I'm trying to get to cubic centimeters. So what I want to get to right before that is grams. And then I can do this with the density. And from atoms, I'll go to moles and then to grams. So I'm going to find the volume using dimensional analysis, and then I'm going to use this equation to find the edge length. I'm doing this fairly quickly in class, but this is something, might take you a while. But you can practice doing problems like this and you can get better at it. Some people are naturally better at it than others, but everyone can improve. Okay, I'm going to switch colors just so things don't get too mixed up, and I'm going to move this guy. So 2.86 times 10 to the 23rd atoms. In this part, I have 1, 2, 3 arrows, 3 conversion factors. Atoms to moles to grams to cubic centimeters. Atoms to moles to grams to cubic centimeters. There's Dora hopping along with her backpack. I'm going to put atoms down here, so those cancel out. And moles down here, so those cancel out. And grams down here, so those cancel out. Well, I was given this, so this is probably going to show up somewhere. And over here, I have those units together, grams and cubic centimeters. So 4.5 is with gram. Gram is on the bottom, so I write 4.5 on the bottom with gram and 1 cubic centimeter. Moles and atoms, like dozens and eggs. 1 mole is how many atoms? 6.022 times 10 to the 23rd. Grams to moles. Where do we find that? Periodic table. Titanium. What's the symbol for titanium? Ti. Make sure that you get Ti and not TL. TL is down here. That's different. Ti is up there. 47.867. So 47.867 grams is 1 mole. That's only true for titanium. Okay, so we'll calculate this number, 2.86 EE23 divided by 6.022 EE23 times 47.867 divided by 4.5 equals. How many sig figs should this number have? 3. My starting number of atoms had 3, and the density has 3. This is 4, and that's 5. So 3 is the smallest. So I'm going to keep that in mind as I write this number down. 5.05. There's the third significant figure. And then I'm going to write down 2 extras because I am not done. I don't want to round this off yet. There's the volume. So the volume is equal to L cubed. How do I undo something being cubed? Cube root, right? So I need not the square root, the cube root of 5.0518 cubic centimeters. So some calculators, like the 36, has a button that lets you do that. So you put in 3 and then the little square root, root thing, and then the 5.0518 and press enter. 1.71. This is also going to have 3 sig figs. 5.8 or 1.72 centimeters. If your calculator doesn't have that button, take this number and raise it to the 1/3 power. Any questions? Yes?
So for the exam, type of questions, if even if you did all the work with the safety economy, it would still be correct.
I would. So I am going to test you on sig figs on certain problems. Other problems, I want you to try to use the correct number of significant figures. We should always try to do that. But if you did a complicated problem like this and told me it was 1.7158, I wouldn't mark that wrong. If you get this number and it's multiple choice, and that number isn't there, but 1.72 is, you should be okay with, oh, that is essentially the same number as this, and picking that. Okay. Any other questions?